Namaste and welcome to this lecture on mathematical foundations for machine learning. In the last class we looked at the idea of linear dependence. We said that a collection of vectors is said to be a linearly dependent collection if the 0 vector can be expressed as a combination. I mean the linear if there could be multiple non-zero scalars which could result in the 0 vector. That means you have a collection u1, u2, uk and you see that the scalars alpha 1, alpha 2, alpha k such that alpha 1 u1 plus alpha 2 u2 plus alpha k uk equal to 0 implies there could be, I mean if there are non-zero scalars alpha 1, alpha 2, not all of them 0, that means you have some non-zero scalars such that alpha 1 u1 plus alpha 2 u2 plus alpha k uk is equal to 0, then you call such set to be a linearly dependent set. We also said that linear dependent set of vectors implies that there is some redundancy that is involved here, because one of the vectors or one or multiple vectors of the set can be expressed as a linear combination of all the vectors, which means there is a redundancy sitting out there. Now contrary to this or opposite of this is the collection of the linearly independent set of vectors, which we will be looking at. The focus of this lecture is basically the linearly independent set of vectors, which eventually we would see them as generating vectors or the vectors which can be used to generate a vector space. So, we will be looking at the idea of linearly independent set now, and we would develop the idea of basis for a vector space and so on. So, that will be the focus of this lecture. So, what we are going to do is we are going to say this: suppose we have u1, u2, uk such that and we also have vectors. We suppose u1, u2, uk are let us say are vectors, are k n component vectors and let us say alpha 1, alpha 2 etc. alpha k are scalars and let us say okay, we will do this, change this, let u1, u2, uk be k n component vectors and alpha 1, alpha 2, alpha k be scalars. Then I am going to look at the linear combination alpha 1 u1 plus alpha 2 u2 plus etc. alpha k uk is equal to the 0 vector n component vector. I will write this as 0 n. Suppose we look at this. So, look at the linear combination that results in the 0 vector, that results in 0 n, the 0 vector, right. So, which means we want to look at alpha 1 u1 plus alpha 2 u2 plus alpha k uk is equal to 0 n, that means the n component vector. If the linear combination is such that, let us write this. So, if the linear combination is such that, if the above linear combination is such that the only way to get the 0 vector is by making the scalar 0. Then we say that u1, u2, uk are linearly independent vectors. Right. We say that u1 u2 uk, the only combination, the only way to get the 0 vector is by making the scalar 0. That means all the scalars alpha 1, alpha 2, alpha k must necessarily be 0 in order to get the 0 vector. If that is the case, then you call such a set of vectors to be linearly independent set of vectors, right. Okay, for example, let us say u1 is equal to 2 1 and u2 is equal to 1 2. Then I want to look at alpha 1 into 2 1 plus alpha 2 into 1 2 is equal to 0 0. The only way in which you can get the 0 vector is by making implies alpha 1 is equal to 0 and alpha 2 is equal to 0. You can try out for this particular case, there is no other combination alpha 1 alpha 2 that would actually give me the 0 vector, in which case we say that 2 1 and 1 2 are linearly independent. So, we say that u 1 and u 2 are linearly independent, right. So, this is what we have. So, what is the only way in which you get the what is the only linear combination that would yield the 0 vector? The only linear combination that would yield the 0 vector is by making the scalar 0, right, which means it also says that look, a linearly independent set cannot contain the 0 vector. So, let us make some interesting observations, some observations. Number 1, linearly independent set cannot contain the 0 vector. Two, what is interesting here is a single vector is always linearly independent unless it is the 0 vector. Right, because if the vector is non-zero vector, then the only way in which you will get the 0 vector is by making the scalar 0, and the moment the single vector is going to be a 0 vector, then that fellow is going to be already a linearly dependent set. So, this is more important, this is one of the most important things that you need to know. So, I mean in a sense it also says that look, the only way you can get you can map all these vectors to 0 vector is by making the scalars 0. So, that is the other interpretation that we have. Okay, one more critical observation that we have, point number 3, any subset of a linearly independent set, any subset of a linearly independent set of vectors is always linearly independent. Right, and even more important and interesting observation that we have here is basically this fourth one, any superset of a linearly dependent set of vectors, dependent set of vectors is linearly dependent. One more observation that we will make, which is going to be the following: two vectors are linearly independent if one is not a multiple of the other. Now, what does this mean? Geometrically this is very interesting to see. Suppose I just take let us say R2, the xy plane. So, I have my x1 axis and I have my x2 axis. Now, what it says is, look, suppose I have this vector which is u. If I say that there is another vector v and the pair u and v are linearly independent, then u and v must be in two different directions. This must be the vector v, or it could be anywhere else, it is not along the direction of u. Now, the moment you say they are linearly dependent, there are two vectors and they are linearly dependent, in which case what happens is the second vector must be along the same direction of the first vector, or the two vectors must be in the same direction. So, this implies for two vectors to be linearly dependent, for any two vectors to be linearly dependent, they must be in the same direction. However, if you have multiple vectors, it becomes a bit difficult to check whether they are linearly independent or dependent. There are various techniques by which you can figure out if the vectors are linearly dependent or independent. For example, you just have, let us say 3 component vectors, you have 3 component vectors or 3 vectors from R3, and you want to figure out if the 3 vectors are linearly dependent. You can put these 3 vectors inside a matrix, or you can construct a matrix with these 3 vectors and then find out the determinant of the matrix. If the determinant of the matrix is not 0, then the 3 vectors are linearly independent. If the determinant is 0, then the 3 vectors are linearly dependent. So, that is what we have, right. And if you have more than 2 vectors, it is not just that you say that the 3 vectors must be in 3 different directions. For example, it can get even a bit confusing. For example, you look at these 2 vectors u and v, the resultant of these vectors u, which is basically u plus v, could actually go and sit somewhere else, it could actually go and sit somewhere here. This could be the vector u plus v. Now, it could be clearly misguiding because u, v and u plus v are in 3 different directions. Therefore, do you want to say that they are linearly independent? No, because u plus v is basically a combination of u and v. Therefore, if you have more than 2 vectors, if you have 2 vectors, you just need to check whether the vectors are multiples of each other for linear dependence. If you have more than 2 vectors, then you must also check if any of the vector is actually a combination of the other vectors. Any 1 or 2 or multiple vectors are going to be expressed as combinations of the other vectors. If they can be expressed as combinations, then the set is going to be linearly dependent set tells us this set is going to be linearly independent. Now, why is there so much emphasis, or why is there this idea of linearly independent set more important? The linearly independent set is more important because we are going to define something interesting here. Okay, let us do that. The first thing that we want to look at is basically we want to define a very interesting term. We want to look at the span of a set of vectors. Span of a set of vectors. The span of the set of vectors is nothing but, say suppose you have this, let u1, u2 etc. uk be k vectors. I do not really know whether it is going to be linearly independent or dependent. I am just going to say these be k vectors, n component vectors. So, the span of these vectors, the span is basically nothing but the set of all possible, the span of these vectors is basically the set of all possible linear combinations of u1, u2, uk. Linear combinations of u1, u2, uk. So, this is what you call a span. That means you take these vectors and then look at all possible linear combinations and put all the possible linear combinations inside a basket, and that basket is what you are going to call as the span. And what is interesting is the span of a set of vectors is going to be a vector space. The span of a set of vectors is going to be a vector space. So, this span is going to be span is a vector space. Right. Now, I want to look at the span of a set of linearly independent vectors. So, let us look at very specific. I want to look at the span of a set of linearly independent vectors. A set of linearly independent vectors, right. A span of set of linearly independent vectors. What happens if you look at the I mean if you just take a collection of linearly independent vectors, let us take this, let v1, v2 etc. vn be linearly independent set of vectors. Right, v1, v2, vn be a set of linearly independent vectors. What is interesting is how do we define the span? The span is nothing but, let us call this span is nothing but the set of all possible linear combinations. So, I am going to write this as sigma alpha I v I is equal to, let us say, I mean just look at okay, for all values of, let me put it this way, take it as 1 to infinity, you can put whatever I am just going to write this as alpha 1 u1 v1 plus alpha 2 v2 plus etc. plus alpha n vn, alpha I real number. So, for I is equal to 1 to n, right, for I is equal to 1. So, this is basically the set of all possible linear combinations of this v1 to vn. Now, what is this span for this linearly independent set of vectors is we are going to say that this is going to be the smallest, this is nothing but the smallest subspace that contains, this is the smallest subspace that contains the set of linearly independent vectors. Okay. This is the smallest subspace that contains the set of linearly independent vectors. So, this is more a very interesting thing that we see. For example, let us consider u1 is or v1 is equal to 2 1 and v2 is equal to 1 2 and v2 is equal to 1 2. Now, what we are going to see is we are going to look at the set of all possible linear combinations alpha 1 v 1 plus alpha 2 v 2 for different scalars alpha 1 alpha 2 and a real number. That means, I am going to look at this alpha 1 into 2 1 plus alpha 2 into 1 2 for different values of alpha 1 alpha 2. Now, what are we going to get? The only combination that would give the 0 vector is by putting alpha 1 is equal to 0, alpha 2 is equal to 0, and therefore, if you keep changing the values of alpha, you are going to get multiple different destinations or multiple different, you are going to get really different vectors every time you keep changing the values of alpha 1 alpha 2, and you have infinitely many values for possible for alpha 1 and alpha 2, because that is going to be any real number. Alpha 1 alpha 2 can take any real value, therefore, you are going to have infinitely many combinations, and you see that the smallest vector space. So, this means it will contain the 0 vector and the span. Okay, so let us look at the span. The span is basically, suppose if you put in this case span of 2 1 1 2, if you look at this, in this case if you see, so the span of 2 1 1 2, first of all we see that the 0 vector, when you put alpha 1 is equal to 0 and alpha 2 is equal to 0, we see that the 0 vector is present in the span of 2 1 and 1 2. Yeah, that means you can write 0 vector as a linear combination of 2 1 and 1 2, that is there. Then what you see is very interesting here. You take, you just want to see whether the span is closed under vector addition. Of course, yes, because you take scalar multiple of 2 1 and scalar multiple of 1 2 and then add them. Where is this linear combination for different values of alpha 1 and alpha 2 going to reside? It is again going to be in the span, because span we have defined it to be the set of all possible linear combinations. Therefore, the span is closed under span of 2 1 1 2 is closed under vector addition, is closed under vector addition, and any scalar multiple of 2 1 and any scalar multiple of 1 2 if you take, that would still be there in the span. In the sense, you can put, suppose if you put alpha 2 is equal to 0 and you keep changing the value of alpha 1, they are all going to be multiples of the vector 2 1, and that is going to be there in the span. And you put alpha 1 is equal to 0 and then keep changing values of alpha 2, therefore, the multiples of 1 2 will also be there in the span. Therefore, the span is going to be closed under span of 2 1 1 2 is closed under scalar multiplication. Therefore, we see the span is basically a vector space closed under scalar multiplication. Therefore, we say that the span of 2 1 1 2 is a vector space. Now, what is interesting is, it is not just the meaning of span saying it is a linear combinations of these two vectors, but what it says is the span of this vectors 2 1 and 1 2 is basically generated by 2 1 and 1 2, the multiples and the linear combinations of 1 2 and 2 1. That means the span of 2 1 1 2 is going to be the entire R2 space that we have, and therefore, these two vectors 2 1 and 1 2 seem to serve as the building block for generating all the vectors in R2, right. This is basically a generating set for the entire R2. That means, you take you take any two linearly independent vectors. Now what it does is take the linear combinations, put all the linear combinations inside a basket, and that is going to be a vector space. By saying that I am going to put linear combinations, basically I am trying to generate each and every vector in that particular vector space as a linear combination of these two guys. Therefore, these two guys seem to be generating the entire vector space. These two guys, the linear combinations are generating the entire vector space, and therefore we are going to call any set of linearly independent vectors, we are going to call them for as a basis for the vector subspace. So, we are going to give a new name, we are going to say that look, a set of n linearly independent vectors, a set of n linearly independent n component vectors is called a basis, for let us say the vector space that contains these n vectors, that contains these n linearly independent n component vectors. Okay. So, this is the most important aspect of it. That means, how many vectors are there, for example, in this span of 2 1 and 1 2, we have infinitely many vectors, and how are these infinitely many vectors generated? They are generated as a linear combinations of 2 1 and 1 2, and what we will see is, if you want to find out what is the transformation or what is it to transform or what is the effect of a transformation on the entire R2, find out what is the transformation doing to the vector 2 1 and to the vector 1 2. If you know that what is the transformation happening to 2 1 and 1 2, any other vector is going to be expressed as a linear combination of these two vectors, therefore you can study the effect of the transformation on the entire set of vectors. Therefore, now we are going to answer that question, what is the strategy that you would want to adopt in order to study the effect of a transformation on an entire vector space? The strategy is to find out what is the transformation doing to the basis vectors. Once you know what it does to the basis vectors, you know what it does to the entire vector space, because that is going to be the entire vector space is generated as a linear combination of the basis vectors. Is that clear? So, find out what happens to the basis, and what is a basis? Basis is nothing but a set of linearly independent vectors for a vector space or for a subspace, vector subspace. Okay. I will say vector subspace here, right. I will say vector subspace that contains the n linearly independent n component vector. So, the basis serves as a sampling set. You remember the question that we asked was, look, if I want to give vaccine to the entire population, what I do is I choose people and with different what would you call health conditions, age group, gender, and a lot of other things, and then I try to inject this vaccine to these people and then kind of study what is the vaccine trying to do to these people, and then you say that the entire population, this could be the possible effect. Therefore, what I do is this basis serves as a sampling set for the vector space. So, let us write that. So, the basis is nothing but a sampling set, it generates, it is a sampling set for a vector space or a vector subspace. And what is interesting is, when you say that you have a set of vectors which form the basis for a vector space, any vector in the vector space will have a unique representation in terms of the basis. Okay. So, let us write this. Suppose let us say u1, u2, uk are linearly independent vectors, and let us say we let x be equal to, let us say alpha 1 u1 plus etcetera plus alpha k uk. That means you are writing x as a linear combination of u1 and u1 to uk vectors. Let x also have another what do you say, another way of representing another let us say another representation in terms of u1, u2 etcetera uk. That means, now I am going to say x is equal to beta 1 u1 plus beta 2 u2 plus etcetera plus beta k uk. Let me call that as 1 and let me call this as 2. Now, if I do 1 minus 2, I basically get the x vector minus the x vector, which is going to give me the 0 vector. The 0 vector gives me alpha 1 minus beta 1 into u1 plus alpha 2 minus beta 2 into u2 plus etcetera plus alpha k minus beta k into uk. Now, x minus x vector is basically the 0 vector. So, the 0 vector is going to have alpha 1 minus beta 1 into u1 plus alpha 2 minus beta 2 into u2 plus etcetera plus alpha k minus beta k into uk. Now, we know that since u1, u2, uk are all linearly independent, since u1, u2 etcetera uk are linearly independent set of vectors, something interesting happens. What is that? The 0 vector has only one representation, wherein which the scalars are all 0. The scalars alpha 1 minus beta 1, alpha 2 minus beta 2 etcetera alpha k minus beta k are all 0, Now, that implies alpha 1 is equal to beta 1, this implies alpha 1 is equal to beta 1, alpha 2 is equal to beta 2 etcetera alpha k is equal to beta k, which means this implies any vector when expressed as a linear combination of a linearly independent set of vectors has a unique set of scalars, This is clear. That means, when you look at basis, the thing is, when you look at a basis, every vector in the vector space will have a unique representation in terms of the basis vectors. That is what we are trying to say. So, what we are going to do is we are going to extrapolate this. We say this implies any vector in a vector space in a vector space or a subspace, you can look at that. Any vector space has a unique representation in terms of the basis. In terms of the basis vectors, right. For example, you just take this, suppose you have this for example, you are going to for example, you have, let the vector space be equal to R2 and I am going to look at basis B1, which is say 2 1 1 2. Now, suppose I take this vector V, which is equal to, let us say 3 3, this can be expressed only alpha 1 into 2 1 plus alpha 2 into 1 2 implies alpha 1 is equal to 1 plus alpha 2 is equal to 1, and this scalars alpha 1 and alpha 2 for this particular vector is unique, right. So, the vector, any vector in terms of the basis will have a unique representation, right. Therefore, the question that we are trying to answer in the previous case, like because it has unique representation, because every vector in terms of basis expansion has unique representation. Now, what you do is, if you want to find out the effect of the transformation on the entire vector space, find out the effect of transformation on the basis vectors, because every other vector is going to be a unique representation in terms of the basis. Now, but we really want to understand better of what a basis is. So, and how many bases can exist for a vector space? You can have infinitely many bases to exist for the vector space, but what is interesting is the number of linearly independent vectors, the number of vectors that get into the basis would remain the same for every basis for a vector space. So, we just look at it. So, for R2 or let us say for any Rn, okay, consider the vector space Rn for any n. Let us take this. Consider the vector space V is equal to R n for any n, right. For any n, what is interesting is we will note down that there are infinitely many bases for Rn. For example, if you take Rn, n is equal to 2, R2 1 0 0 1 is a basis, 2 1 1 2 is another basis, 2 3 4 7 is another basis, 1 root 2 then root 7 6 is another basis. You have multiple bases like this, but what is interesting is every basis has only the same number of vectors. However, so we write this, however all the bases will have exactly n vectors, right, and this n is therefore called the dimension of the vector space. That is an important thing. So, the number of elements in a given basis, the number of elements, or I will say number of vectors in any given basis for a vector space is called the dimension of the vector space. Right. This is called the dimension of the vector space. So, now what do we have? We figured out what is a linearly dependent set, we figured out what is linearly independent set, we figured out why we need to look at linearly independent set, we looked at what could the linear combinations of the linearly independent set generate. It generates a vector space, and we said that look, the moment you generate all the vectors in the vector space, you can again pick n linearly independent vectors other than the ones that you used to generate. And so what we said is this set of n, the set of linearly independent vectors would form the basis, and the number of elements in the basis is called the dimension of the vector space. So now what we do is we will stop here, and when we come for the next lecture, we will also get some kind of an intuition or some kind of insights into this basis, and we will look at vector space. Why is this basis important, especially from the perspective of machine learning? What is this, why is this number a very important number? We will look at it in the next class, and with that, this module week 1 corresponding to vector space, vector subspaces, linear independence would get over, and in the next week we will start with linear combinations. We will try to get some more insights about basis, the geometrical meaning, then you get some probably some examples, we will look at it, and then we will move on to the next module which is basically on linear transformations. Thank you.